Hello friends, I welcome you in lecture number 20 on Laplace transform. In last lecture we have talked about inverse Laplace transform and we have seen inverse Laplace transform formulas for some standard functions. So using those formulas we try to find out inverse Laplace transform of these functions. We start with this first function 5 times s divided by s square minus 25. So we have to find out inverse Laplace transform of this function 5s divided by s square minus 25. So this I can rewrite as 5 times L inverse of s divided by s square minus square of 5. So I have to think that this function s divided by s square minus 5 square is Laplace transform of which function of t. So if we recall, we had seen this formula in the last lecture that L inverse of s divided by s square minus a square is cos hyperbolic at, because Laplace transform of cos hyperbolic at is s divided by s square minus a square. Therefore, L inverse of s divided by s square minus a square is equal to cos hyperbolic at. So, if we compare with this a equal to 5, therefore, this is cos hyperbolic 5t. So, we have to remember the formulas for Laplace transform, and using those formulas we can easily derive the corresponding formula for inverse Laplace transform. So we will remember this formula: Laplace transform of cos hyperbolic at is s divided by s square minus a square, and using this we can derive the formula for L inverse of s divided by s square minus a square, which is cos hyperbolic at, and here a equal to 5. We consider another function s minus 4 divided by s square minus 4. So we have to write our function in terms of those functions whose inverse Laplace transform is known to us. This I can rewrite as s divided by s square minus 4 minus 4 divided by s square minus 4. Again I can rewrite this as s divided by s square minus 2 square minus 4 times 1 divided by s square minus 2 square. Now I again recall that L inverse of s divided by s square minus a square, this is cos hyperbolic at, as we just discussed in previous function. And if we have 1 over s square minus a square form, then we recall that Laplace transform of sin hyperbolic at divided by a is 1 divided by s square minus a square. Therefore, L inverse of 1 divided by s square minus a square will be equal to sin hyperbolic at divided by a. So this second function is in this form with a equal to 2. So now L inverse of s minus 4 divided by s square minus 4, this is equal to L inverse of s divided by s square minus 2 square minus 4 times L inverse of 1 divided by s square minus 2 square. Now this first one is cos hyperbolic 2 times t minus 4 times. For this second one we use this formula L inverse of 1 divided by s square minus a square equal to sin hyperbolic at divided by a, and if we compare we have a equal to 2 Therefore, L inverse of 1 over s square minus 2 square is sine hyperbolic 2t divided by 2. And here we can cancel out this 2 with this 4, and required inverse Laplace transform is cos hyperbolic 2t minus 2 times sine hyperbolic 2t. So sometimes if we don't have ready-made formula for given function, then we have to rewrite our function in terms of those functions of s whose inverse Laplace transform formula is known to us. We don't have any formula for this function, so we are writing this function as s divided by s square minus 4 minus 4 divided by s square minus 4, and we have formula for these two functions, and using linearity property we are able to decide the L inverse of s minus 4 over s square minus 4, and it is cos hyperbolic 2t minus 2 sine hyperbolic 2t. Now next function is 2.4 divided by s raised to 4 minus 228 divided by s raised to 6. So L inverse of this function, L inverse of 2.4 divided by s raised to 4 minus 228 divided by s raised to 6, this is equal to, using linearity property, 2.4 times L inverse of 1 divided by s raised to 4 minus 228 times L inverse of 1 divided by s raised to 6. So we must have the inverse Laplace transform formula for 1 divided by s raised to n. So if you don't remember, you can derive this formula using the formula for Laplace transform of t raised to n. We know that Laplace transform of t raised to n is given by n factorial divided by s raised to n plus 1 if our n is natural number. Now here we require s raised to n, so from this we can write that Laplace transform of t raised to n minus 1, here we replace n by n minus 1, will be n minus 1 factorial divided by s raised to n minus 1 plus 1, that is s raised to n. Now this n minus 1 factorial is constant, so therefore we obtain that L inverse of 1 divided by s raised to n is equal to t raised to n minus 1 divided by n minus 1 factorial. We take this constant on this side, and because it is constant we can take it inside the Laplace transform, and then we take inverse Laplace transform on both sides, or we are using the definition. Okay, here one more step is Laplace transform of t raised to n minus 1 divided by n minus 1 factorial equals 1 over s raised to n. Therefore L inverse of 1 over s raised to n is t raised to n minus 1 divided by n minus 1 factorial, provided n is a natural number. So we can use this formula now with n equal to 4 and n equal to 6. So for n equal to 4 we will have 2.4 t raised to n minus 4, that is 4 minus 1 divided by n minus 1 factorial. Okay, if we take n equal to 4 here, we will have t raised to 4 minus 1, that is t raised to 3 divided by 4 minus 1 factorial, that is 3 factorial, minus 228. Here we have n equal to 6, so we have 6 minus 1, that is t raised to 5 divided by 6 minus 1 factorial, that is 5 factorial. And we can further simplify this. 3 factorial can be written as 3 into 2 minus 228, and here I can rewrite this as 5 into 4 into 3 into 2 into 1. Okay, fine. Now we try to cancel out whatever we can cancel. Here 3 into 2 is 6, and if we multiply 6 by 0.4, then we will have 6 into 4 24, and we have this 0.4 because so we have 2.4. So this will cancel out and we will have 0.4 times t raised to 3. Now this 228, so we can write 228 as 57 into 4. So you can check 4 into 7 is 8, and then 4 into 5 20 plus 2, that is 228. Again we can write this 57 as 19 into 3 into 4. So we have 19 times 12. So we can cancel out 12 here. 3 into 4. So we are left with here 19, and here 12 will cancel out, and we have 5 into 2, that is 10 t raised to 5. So finally we obtain this 0.4 t raised to 3 minus 1.9 t raised to 5. So this is inverse Laplace transform of this function. We have simply used this formula and linearity property. L inverse of 1 divided by s raised to n equal to t raised to n minus 1 divided by n minus 1 factorial. N belongs to n. Next function is 60 plus 6x square plus s raised to 4 divided by s raised to 7. So this also we write in the form 1 over s raised to n. So we have 60 times 1 over s raised to n s raised to 7 plus 6 times s square upon s raised to 7, that is s raised to 5, plus 1 divided by s raised to 7 minus 4, that is 3. Now we apply that formula which we just applied. L inverse of 1 divided by s raised to n is t raised to n minus 1 divided by n minus 1 factorial if power is a natural number. So here all the powers are natural number, as 7, 5 and 3 all are natural numbers. So we simply apply that formula. Therefore inverse Laplace transform of 60 plus 6 times s square plus s raised to 4 divided by s raised to 7. Now we directly write 60 times L inverse of 1 over s raised to 7, that is t raised to 7 minus 1 6 divided by n minus 1 factorial, that is 7 minus 1 factorial, which is 6 factorial. Similarly 6 times 1 over s raised to 5. So if we have 5, we will write 5 minus 1, that is 4 divided by 4 factorial, plus here we have n equal to 3. So this is t raised to 2 divided by 2 factorial. Now we try to simplify. This is 6 0 t raised to 6. Here we will have product of 6 5 4 3 2 and 1, and we will have 5 into 2 10 into 6 60. So that 60 will cancel out here. Similarly here we have t raised to 4 times 4 into 3 into 2 into 1. So this 6 will cancel out here, and plus t square divided by 2 factorial, that is 2. Now if we cancel out 60 here, we will cancel out 5 2, that is 10 into 6. So we are left with 4 into 3, that is 12. T raised to 6 divided by 12, plus here we will cancel out this 3 and 2, and 6 will cancel out. So we are left with t raised to 4 divided by 4, and here we have t square divided by 2. So if we wish, we can take LCM, or we can keep this as it is. So this is another application of this formula, L inverse of 1 divided by s raised to n equal to t raised to n minus 1 divided by n minus 1 factorial. So we proceed further now. S divided by L square s square plus n square pi square. So this n, pi, L all are considered as constants. We have function of s here. So this n, pi and L are constants. Now we have formula for inverse Laplace transform of s divided by s square plus a square. We know that this s divided by s square plus a square is Laplace transform of cos 80. Therefore, L inverse of s divided by s square plus a square is cos 80. But this is not in this form. Here coefficient of s square is not 1, it is L square. So first we have to rewrite this function in this form so that we can use this formula. We require coefficient of s square to be 1, so we take L square common and we can write this as we divide by L square. So this we can rewrite as we divide, or first we write this as s square plus n square pi square divided by L square, and if I multiply this by L square, then we can see this is going to be L square s square, that is correct, plus L square will cancel out with this L square and n square pi square. So this is I have written in another form. Because I require coefficient of s square to be 1, I take L square common here. So here I have to divide this quantity by L square. So this is now in that form. This 1 by L square is constant now, and this I can rewrite as s divided by s square plus some constant square n pi divided by L whole square. And we know that inverse Laplace transform of s over s square plus a square is cos 80. So now we can use this formula with a equal to n pi divided by L. Therefore, L inverse of s divided by L square s square plus n square pi square, this is equal to this 1 divided by L square. Inverse Laplace transform of this function will be equal to inverse Laplace transform of this function. 1 by L square is constant, and we use this formula, and if we compare with this, a equal to n pi divided by L. So this is going to be cos n pi divided by L times t, cos 80, a equal to n pi divided by L. So if we want to use this type of formulas, then s square has coefficient 1. So if your coefficient is not 1, first you make it 1 by taking it common. Here I have taken L square common, so here I divide by L square. Now this 1 by L square is constant, so we will keep it aside and we will find 1 by L square times L inverse of this function. And because it is in this form with a equal to n pi over L, its inverse Laplace transform is cos 80, where a equal to n pi by L. And we consider one more problem. 1 divided by s plus square root of 2 times s minus square root of 3. So we don't have the formula for this type of product, ready-made formula, but we have this type of formula, L inverse of 1 divided by s minus a, this is equal to e raised to at, because Laplace transform of e raised to at is 1 divided by s minus a. So we have to arrange this function in that form. For that, what I can do is, here I keep these two as it is, s plus square root of 2, s minus square root of 3, and in the numerator I take difference of these two, s plus root 2 minus s minus root 3, but difference of these two will be square root of 2 plus square root of 3, and here we have 1. So if here s will cancel out and I will be left with square root of 2 plus square root of 3. So to adjust this, I have to multiply by 1 divided by square root of 2 plus square root of 3, so that this difference will be s will cancel out and root 2 plus root 3, so that will cancel out with this one, 1 divided by root 2 plus root 3, so that this is correct representation of given function in another form. Now this I can rewrite as 1 divided by square root of 2 plus square root of 3, and now I divide s plus root 2 by this product, and I will be left with 1 divided by s minus root 3. Similarly, I divide s minus root 3 by this product, and I will be left with 1 divided by s plus root 2. And I know the formula for inverse Laplace transform of both of these functions. So in the next step, we write down their inverse Laplace transform. Therefore, L inverse of 1 over s plus root 2, 1 over s plus root 2 times s minus root 3, this is equal to L inverse of this bracket multiplied by 1 divided by square root of 2 plus square root of 3. So it is constant, it will be outside this 1 divided by square root of 2 plus square root of 3 into inverse Laplace transform of 1 divided by s minus root 3, that is e raised to at, with a equal to root 3 here, and this is e raised to minus root 2 times t. If we compare with s minus a, then s plus root 2 can be written as s minus root 2. So we consider, here we consider e raised to minus root 2 t, and we complete this bracket, because Laplace transform of e raised to minus root 2 t will be equal to 1 divided by s minus root 2, that is plus root 2. Okay, fine. So in this way we can use standard inverse Laplace transform formulas to obtain the inverse Laplace transform of this type of functions. So I think here we have used almost all the formulas of standard inverse Laplace transform. So I stop here, and we will continue this in the next lecture. Thank you very much.